Hey everybody, and welcome to the first How I Made video, a series in which I narcissistically recount my experiences learning a specific topic in hopes that people find it interesting or entertaining. I wanted to call this series Coding Explorations. Well, that sounds a little bit too close to Sebastian Legg's series name, and I'd like to be a little bit different, so I think the name of these videos is kind of tentative at the moment. These videos aren't meant to be a tutorial, but serve as a sort of video diary or as potential inspiration for people. But for today's topic, we'll be discussing Minecraft shaders, or more specifically, improving Minecraft's existing shaders. For the uninitiated, a shader refers to a program that is run on the GPU, usually for graphics. So when I talk about Minecraft shaders, I'm talking about the code that is executed on the GPU that decides what Minecraft looks like when it shows up on your screen. These programs usually start with lighting calculations, so you can determine what is actually visible in the scene, and this is commonly referred to as a lighting model. Minecraft's lighting model in the base game is extremely basic, mainly because it didn't need anything more. The developers of Minecraft chose to utilize something called a Lightmap that stores how exposed a block is to the sky, as well as if it is lit by a nearby light-emitting block like a torch or glowstone. This is combined with an ambient occlusion technique that smooths light levels across a given block in order to darken the corners. This creates a simple, pleasing lighting that is also really quick, which allows the bulk of the resources to be used by the procedural generation. Since this light map is provided to us in the shaders, we can visualize it by coloring blocks based on their light map values. As you can see, the green color is how exposed a block is to the sky. The blocks under the tree are less exposed, therefore they receive less light. In addition, we have the red color, which is how lit the block is by any nearby light source. I think this technique is really interesting as it tricks a lot of people into thinking Minecraft has shadows when it really doesn't. Now that we know how Minecraft lighting works conceptually, we can move on to actually improving it. But first we need to recreate the Minecraft base shaders. Here we have the base pixel shader. As you can see, we sample the block texture and then we set that as the outputted pixel color. Visually, this gives us Minecraft without any lighting, but the blocks all look correct. To get the lighting of base Minecraft, we need to introduce the lightmap values. Thankfully, the lightmap is computed by the CPU and then it's passed over to the shader, so we don't actually have to do any work to create the lightmap, except that the lightmap values aren't in the 0 to 1 range automatically, so we actually need to transform it into that range with the following simple calculation. Using the light map values, we are able to construct a light color to apply to the block. Let's say we have a sky color and a torch color of our choice. We then multiply those two colors by their corresponding light map values, and then we add them together. And then we multiply our base block color by this light color, and we get Minecraft. Here's an example of an unlit structure with and without the sky exposure involved, and then an example of torch lighting with and without torch light values involved. Now that we have a base shader to work with, we can move on to actually improving the lighting. A simple first step is to modify how this light map attenuates. Now, I'm not sure if this is true or not, but I'm going to assume that the sky exposure is a linear gradient. Linear gradients usually look bad, and exponential transitions are generally more pleasing. To modify this, we can multiply the sky value by itself any number of times. This works because the sky and light exposure values are in the 0 to 1 range, and when you, for example, square a number like that, the result becomes lower than its original value. I chose to cube the sky exposure because I liked it. Next is the light values from blocks. This is also a linear gradient, I think. Using the form kx to the n, where k is the brightness of the light source and n is the rate at which it depreciates, We can customize how bright the light is at the source and how quickly the light fades. I chose a value of 3 for K and a value of 4 for N because I liked it. Here's a before and after for the sky exposure changes. As you can see, the exposure dies off much quicker, so blocks become darker faster. And here's the before and after for the torch changes as well. The torch visually looks brighter, but it also doesn't light up as many blocks. It's a very minor change that we've made here, but in my opinion, it already looks much better. Moving on from the light map, we can work on modeling diffuse light. Now, diffuse light is the light that is scattered by a surface when lit by a direct light source. Pretty much all the light we see in day-to-day life is diffuse lighting, as it's the light that is reflected off a surface after it has been modified and scattered by the material. It's like what makes a leaf look green to you. Let's say you have a directional light source and a surface, then the amount of diffuse light reflected by the surface is the angle between the surface and the direction of the light. This method of calculating diffuse light is known as the Lambertian diffuse model, for anybody that cares, and it's definitely not the best, but it's fast and it works for a simple game like Minecraft. Now, if you recall from earlier when I was discussing the light map, I mentioned sky exposure and not sun exposure. That's because the sun in Minecraft doesn't actually mean anything, and it's purely for show. If you've been tricked, then congratulations, the Minecraft developers did a great job. Thankfully, we can remedy this. Our shaders are provided with the direction of the sun, which is half of the diffuse lighting formula. Next, we need the direction at which light should reflect off of a surface. This direction is known as a normal vector, and is also provided to us in the same way that the texture of a block is. Now, both of these vectors are of unit length, which means that their parts sum to 1, and coincidentally, the dot product of two unit length vectors is the cosine of the angle between them, which means taking the dot product of these two vectors gives us how much light is reflected by the block. If the direction that the light bounces is in the opposite direction of the light, then our dot product gives us back 0, and when we multiply a color by 0, well, we get black, which means it is unlit. And here's what our shaders now look like with the Lambertian diffuse applied. It's a bit hard to notice the shading. Obviously it's brighter, but the effect is easier to notice when the time in-game is set to noon. Since the sun is directly above the blocks, the sides of the blocks become half as bright as the top. While I like the diffuse lighting as it is, I wanted to modify it a bit more to make it my own. I introduced a sun color into the mix as well as modifying some of the math, and the results are more pleasing in my opinion. The sun color causes the lit areas to be warmer than the unlit, and the math modification makes it overall a bit brighter and pleasant to look at. Now, I've been hiding the truth from you here, and instead our diffused lighting has quite a big issue. Our shaders are indiscriminately throwing out diffused lighting to everybody who asks for it, regardless of if the block can actually see the sun or not. And this is quite obvious when you look at areas that very clearly should be hidden from the sun. This problem isn't actually solvable, as we have no way of knowing if a block is truly hidden from the sun, but we do have a way to mitigate this, and it's with our handy-dandy light map. By multiplying our diffuse lighting by the sky exposure, we can prevent our diffuse lighting from having any effect on the blocks that should be unaffected by the sky. And with this, our diffuse lighting is basically complete, and we can finally move on. The last part of our lighting model is something that many people probably haven't noticed Minecraft lacks, and that's actual shadows. I'm going to be rather brief about shadows, as it's a lot of math and technical stuff, but the general idea is that for each light source in a scene that you want to cast shadows, you render the scene from that light's point of view. The renderer then writes how far away each object is from the light source, stores this information, And then by combining the depth information of the actual scene and from the point of view of each light source, we can determine if a point in space is seen by both the camera and the light, and if it's not seen by the light, then that point is within shadow and we can color it accordingly. Here's our shaders with the shadows included, and the difference here is probably the most noticeable out of any effect in this video. Unfortunately for our computers, shadows are extremely expensive to compute, and next time you're playing a game, you should try to notice what is and isn't casting shadows. It's kind of fun, I think. That wraps up my improved lighting model for Minecraft. It's not super advanced, but it satisfies my goal as an overall improvement. Here's the base shaders we started with, and here's where we're at. I think it looks a bit better, but now we can move on to post-processing, which are visual effects we apply after a scene has been rendered, but like before it's presented to the actual screen. Now, before we continue, I'd like to talk a little bit about color. You may be used to color channels such as red, blue, and green being between 0 and 255 or 8-bit, and this is how it is pretty much everywhere at a consumer level, like Photoshop for an example. But in graphics programming, colors are in the range of 0 to 1, where black is 0 and white is 1. This simplifies a lot of operations that I'll be discussing shortly. Moving on, the first step in my post-processing pipeline is brightness and contrast. The general brightness and contrast function for a color in linear space looks like contrast times the color minus 0.5 plus 0.5 plus brightness. Essentially, the contrast value acts as the amount of gain that a color experiences. The higher the contrast value, the darker dark colors get, and the brighter bright colors get. When the contrast value is between 0 and 1, colors become much flatter. The brightness in this case is an additive increase to the overall color, and with this effect applied, there's already a pleasing change to the overall appearance of the game, in my opinion. Next up in the pipeline is saturation. Saturation refers to the intensity of a color. An image that is desaturated is black and white, and an image with high saturation is probably very uncomfortable to look at. Creating a saturation filter is actually really easy. By calculating the luminance of a pixel, we know what it would look like if it were desaturated. By linearly interpolating between the desaturated color and its normal self, we can either lower the saturation or overload the interpolation and see what a more saturated version of the color would look like. Here's what the shaders look like with the saturation included. Usually I desaturate my visuals, but I'm trying something new here and actually increasing the saturation. Last up in the color effects you're probably familiar with, we have sharpness. Sharpness is a bit difficult as it requires us to have a blurred version of the render. The way sharpness filters work is they exaggerate the brightness difference between edges in an image. This creates the illusion of higher detail by having more pronounced edge lines. The general formula for sharpness is color plus the color minus the blurred color times the sharpness, where sharpness is how accentuated the brightness difference between the two colors becomes. And now you may be asking yourself, Acerola, where does the blurred color come from? And well, that's with yet another image effect. The blur effect I went with is Gaussian blur. It's pretty costly performance-wise, but my goal here wasn't performance, it was pretty pictures, so onward we go. Essentially, the way Gaussian blur works is we take a weighted average of a pixel and the pixels surrounding it, where pixels farther away from the center pixel have less weight to them. This gives us a much more pleasing blur than other faster blur filters, but the math is, well, it's expensive. This blur technique is going to come into play in the next effect, but first let's look at what the sharpness filter actually looks like when it's applied. As you can see, the image looks like it has more detail to it despite there being nothing new. Personally, I thought it didn't look too great in Minecraft and maybe I could have just ditched the effect, but I went through all this effort, so I kept it. Moving on from sharpness, we have our first real post-processing effect, which is bloom. I had a tough time with bloom as the methods I've used to implement it are not possible in this space as I don't have control over the individual render texture resolutions like I would in Unity. The general way bloom is implemented is you write all of the bright colors of a given scene to a texture and then you blur that and then you reapply it to the original render so that bright colors look like they blend into surrounding pixels. Unfortunately, when I tried this, it just looked bad, and I unfortunately didn't take pictures of it, and I don't know how to recreate it, so I'm sorry, I will next time. But the bloom blur maintained the blocky look, and there was kind of gross hard edges on it, so maybe I could have just blurred it again. I don't know, it's too late. But after labbing on the effect for a while, I decided to blur the entire image once again like I did with sharpness, and then when I added this blurred image back, I weighted the values so that brighter colors add more to the original render. It's not perfect, and I could probably improve the effect more, but I liked how it turned out. Here's the before and after with and without the bloom. As you can see, brighter colors become more accentuated. Next up is a sort of realism effect, which is fog. If you ever look off into the distance in real life, you'll notice how distant objects become faded out or sort of blend in with the sky horizon. And this is due to all the stuff in between you and that object in the distance that obscures the light that ends up going into your eyes. Essentially, the idea here is that objects far away from the camera become foggy. Thankfully, like I explained in the shadows section earlier, we know how far away objects are from the camera, and with this view distance, we can compute a fog factor and use that as an interpolator to transition the original color of an object with a given fog color. The fog color I used is just the sky color, but here's the before and after with and without the fog. This effect is probably my favorite as the effects are very noticeable and really pleasing. At this point, the only thing left to do is apply some gamma correction. Gamma correction is the act of taking a color to a certain exponent in order to make darker colors more dark. The most common gamma correction factor is 2.2, which is referred to as gamma space. Generally, if you want to apply lighting calculations, you invert any gamma correction such that the color goes back to linear space, and then you reapply a gamma correction. And this is why I waited until the end to gamma correct. Personally, I think Minecraft looks really gross with the traditional level of gamma correction, so I ended up going with a much smaller gamma value of just 1.5. This way the colors don't look so washed out, and the contrast has a more of a presence in the scene, but it doesn't get so dark. Now, you may be saying to yourself, Acerola, this looks like shit, dude. And you're right. I've also been slightly hiding how bad it truly looks. When you look at certain blocks like sand, the colors are just too bright and unappealing. And this is where we bring in the real final pass, an effect descended from the heavens to save amateur technical artists from themselves, a technique known as tone mapping. Tone mapping is a general term referring to any sort of conversion of one set of colors to another. Usually it's to try and approximate a higher range of colors into a more limited range. For instance, while I mentioned earlier that in graphics the range of color is 0 to 1, that's not quite true. During all of these shader passes, the colors I write to the render textures in between passes can exceed that range. It is only when they are presented to the screen that they become clamped to this 0 to 1 range, and this is where tone mapping comes in, because we can map that higher range of color into the 0 to 1 range while trying to maintain and approximate that higher range of color. The tone mapping algorithm I found most appealing was the ACES filmic curve, which stands for Academy Color Encoding System, if you care for some reason. This happens to be the default tone mapping function that Unreal Engine uses for its filmic tone mapper, and despite ACES being like the industry standard tone mapper algorithm, I could not find any specific documentation or articles about why it is the way it is. So let me just sum it up for you. Basically, you do a lot of fancy matrix multiplications, and then out comes a much more pleasing range of colors. And with the explanation over with, here's the before and after with and without the tone mapping. And as you can see, this is what really pulls everything together. And in the future, I'd like to experiment more with different tone mappers or maybe even create my own. But this wraps up every effect that went into creating my shaders. Before talking about potential extensions, I'd like to go over all the effects in order one more time. To start, we have the base Minecraft textures, then we have the Lightmap, then we have the diffuse lighting, then shadows, which completes the lighting model, and then onto our color grading, we have contrast, saturation, and sharpness. Then we have our actual post-processing effects, which is bloom, and then Screenspace Fog. And finally, we have gamma correction and then tone mapping. In future videos, I'd like to discuss possible extensions for my projects, should I return to them, but for this one, the possible extensions are like kind of infinite. To name a few, I think improving the weather effects would be a priority. Additionally, these shaders don't work very well for nighttime, which is why I didn't show any screenshots of it. And lastly, a hallmark of most Minecraft shaders is impressive water rendering. So when I learn some of those techniques elsewhere, I think I'll come back and see what I can do in the Minecraft context. But in closing, this was a fun project that had unique challenges, and I think I'm glad I did it. I've never really written a script for a video before or even edited anything seriously, so if you have any feedback, please let me know. Hopefully I'll have some more stuff to show you soon. But I've got to go now. Thanks for watching, and have a good day.